Hey, welcome. Have you ever looked around and just felt like there's a hidden code to everything? Some kind of secret pattern that connects a flower petal, a grand cathedral, and even a tiny snowflake? Well, today, we're going to crack that code.
Just look at these. You've got these amazing patterns in nature, the incredible lines of famous buildings, and art that just pulls you in. We don't even have to think about it, we just find them beautiful. But why? What's the common thread here that our eyes and our brains are locking onto?
Well, it turns out there really is one. It's like this unspoken language of design, a basic rule that decides what we see as orderly and, well, just right. And the cool part is, once you learn to see it, you will start seeing it absolutely everywhere. So let's start pulling back the curtain on this hidden language. So what is it? What is this secret ingredient that makes all these different things feel so visually satisfying? Let's peel back that first layer. And the answer, in one single, powerful word, is symmetry. Yeah, it's a concept from geometry class, but its impact is everywhere. In art, in nature, in our daily lives. Symmetry is the code. It's the big idea that pulls all the different parts of a design together into one cohesive whole. So let's start with the easiest, most gut-level type of symmetry. We can just call it the mirror test. This is the kind you recognize instantly, the kind we've all understood since we were kids.
Okay, so the official name for this is line symmetry. You might also hear it called reflectional or bilateral symmetry. The definition is super simple. If you can draw a line straight down the middle of something and one side is a perfect mirror image of the other, boom, it has line symmetry. And that dividing line, that's your axis of symmetry. And you can actually create this perfect symmetry yourself in like 10 seconds. Remember this old trick? You just grab a piece of paper, fold it in half, put a little drop of ink or paint right on that crease, press it together, and when you open it back up, you get this, a perfect symmetrical shape. That fold line we made, that's the axis of symmetry. It creates a flawless mirror image on both sides. This little ink blot thing is actually the perfect illustration of what line symmetry is all about.
And this idea is built into things you see every single day, like, I don't know, the alphabet. Letters like A or M have a vertical line of symmetry, right? The left half is a mirror of the right. But then you look at letters like F or G, and nope, there's just no way to fold them to get two matching halves. All right, so that's the mirror test. Simple enough. But what about things that don't have a mirror image, but they still feel perfectly balanced? For that, we need a totally different kind of symmetry. Let's call this one the perfect turn.
This is what's known as rotational symmetry. Basically, it's when you can turn an object around a center point, and before you've even gone all the way around in a full circle, it looks exactly the same as when you started.
The hands of a clock are a fantastic everyday example. They're just rotating around that fixed point in the middle. But you also see this with, say, a spinning pinwheel or a ceiling fan. As they turn, they keep hitting these spots where they look identical to how they started. In that point they spin around, that's called the center of rotation. Okay, now this table here breaks it down perfectly. Take a square. If you turn it 90 degrees, just a quarter turn, it looks exactly the same. And you can do that 4 times before you get back to the start, right? So we say it has a rotational symmetry of order 4. For an equilateral triangle, it's a 120-degree turn, and you can do that 3 times. So its order is 3. The order is really just how many times an object looks the same during one full spin. Simple as that. So we've got the mirror test and the perfect turn, line and rotational symmetry. Now let's see how these super simple geometric ideas get used to create some of the most incredible structures in the entire world. Yep, we're talking about architecture. See, architects figured out the power of this bilateral or line symmetry a long, long time ago. Think about it, our own bodies are bilaterally symmetrical, so we subconsciously connect that shape with what feels natural, balanced, and stable. And throughout history, architects have used that to create a feeling of divinity, of power, of perfect order.
Just look at the Taj Mahal or the Alamo. They're such powerful examples. If you drew a line right down the center of either one, the left side is a perfect mirror of the right, and that is 100% not an accident. That symmetry is deliberately used to create this incredible feeling of perfect balance and permanence. But what if you don't want permanence and stability? What if you, as the architect, want to create a feeling of movement? Or what if you want to pull someone's eye towards a central point? Well, for that, you ditch the mirror image and you embrace rotational symmetry. It creates this powerful rhythm that directs your focus right to the middle. And this shows it perfectly. You've got the pentagon with its order 5 rotational symmetry and the lotus temple with its order of 3. Both of these designs just pull your attention directly into the center of the building. They feel dynamic, they feel focused, and it's all thanks to the power of that perfect turn. Okay, so we've seen symmetry in nature, we've seen it in architecture. Now let's look at an artist who took these mathematical rules and just broke reality with them. It's time to talk about the master himself, M.C. Escher. And Escher knew exactly what he was doing. He didn't see it as just clever drawing. He literally called it gymnastics of the brain. He was playing with these really complex mathematical ideas about how shapes can fit together perfectly to create patterns that totally mess with your head. So here we see Escher playing with a whole other kind of symmetry. He's creating patterns not by flipping or turning shapes, but just by sliding them. It's called translation symmetry, and he used it to make his famous tessellations, where you've got these dogs or lizards or whatever interlocking perfectly with 0 gaps or overlaps. It's incredible. But he didn't just stop at one type of symmetry. Oh no. In a masterpiece like this one, Circle Limit 4, he's combining everything. You've got angels and devils repeating through both reflection and rotation. And see how they get smaller and smaller as they get to the edge? He's creating this stunning illusion of infinity, all packed inside one single circle. And in the end, Escher used these rules of geometry not just to make cool patterns, but to build entire worlds that just shouldn't exist. I mean, look at his famous piece, Relativity. You've got staircases that seem to go up and down at the exact same time. He took the predictable, orderly rules of geometry and used them to build these impossibly beautiful realities that completely challenge how we even see the world. So look, here's the real takeaway. Symmetry isn't just some dry, boring math concept. It's a fundamental code for creating balance and beauty, and even for breaking reality itself. We've cracked the basics of that code today: the mirror, the turn, and the slide. So the only question left is, now that you know what to look for, where are you going to see it next?